Hi everyone, welcome to My Max Academy. In this video, we'll continue with for 10th standard CBSE Chapter 1 Real Numbers. We will continue with exercise 1.1, page number 7, problem number 5. So exercise 1.1, page number 7 in your textbook. Page number 7, exercise 1.1, fifth problem. So what fifth problem says is, I'm reading the question. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. So what you have to prove? To prove is, right, cube of any positive integer. Any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. So what we have to prove is, we have to prove that cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. So we have to show this. So what it means is, suppose if we take any cube of any positive integer, suppose let's take 4 cube. 4 cube is what? 64. Then we can write this 64 as any one of the form 9m or 9m plus 1 or 9m plus 8. Right? For example, if you see this, so this can be written as 9 into 7 plus 1. 64 can be written as 9 times 7 plus 1, 9 7s are 63 plus 1, 64, which means it is in the form of 9 into m plus 1. 9m means 9 into m plus, so it is taking this form. So which means you take any positive integer and if you cube that number, then you can write the cube of that positive number in any one of these three forms, 9m or 9m plus 1 or 9m plus 8. That we have to prove in this problem, but it is true, but we are going to prove this. You take any other number. Let's take suppose 3 cube. What is 3 cube? 27. 27 can be written as 9 times 3, which is of the form 9 into m. 9m. 9 into m means 9m. So it is in the form of 9m. Right? Any number. Suppose if you want to take which one shall we take? Suppose if we take 6 cube. 6 cube will come in terms of 3. We can take 7 cube also, or 8 cube. 7 cube. 7 cube is 343. Right? 343 can be written as what? 9 into something. If we divide 343 by 9, what do we get? 9. 9 3s are 27. Then you get 73. 6. 9 7s are 9 8s are 72. You get 1. Right? So this can be written as 9 into 38 plus 1. 7 cube can be written as 9 into 38 plus 1. Right? So which means it is in the form of 9m plus 1. Right? Anything. Suppose if we take 2 cube. 2 cube is what? 8. 8 can be written as 9 into 0 plus 8. 8 can be written as 9 into 0 plus 8, which means it is in the form of 9m plus 8. So you take any cube of any positive integer, you can write that only in either of these three forms. And that we are going to prove here. Right? So solution or proof is, so whenever we want to prove 9m or 9m plus 1 or 9m plus 8, so we take, let a be any positive integer. A be any positive integer. Let a be any positive integer. Now we will always take b as, let b equal to, generally we will take b as equal to this number 9. Whatever form we need to prove, 9m, 9m plus 1, 9m plus 8 means this 9 we will take b as 9. Suppose if we take b as 9, right, then we will have to deal with 9 cases, because when we apply Euclid's division lemma, right, then your r will be taking the value 0, 1, 2, 3, 4, 5, 6, 7, 8. So you will have to deal with 9 cases. So which will make your problem very lengthy. If you watch my previous video, you will know how we proved the earlier problems, right? So either we can take b as 9. In that case, our steps will be more, or we can try to consider the square root of this number 9. What is square root of 9? 3. Let's try for that. Let's try for that number 3. So we will take, let b is equal to 3. Why we take b is equal to 3? Because if we have to generally take b equal to 9, whatever form we need to view, we need to prove. So in the earlier problem also we had the fourth problem, we had to prove the square of the positive integer is of the form 3m or 3m plus 1. There we took b as 3, the given thing. That was 3m or 3m plus 1, we took b as 3. Right? But here we could have taken b as 9 also, or we can still take b as 9. But the number of cases will be more. So we will take the next number that we can try is not 8 or 7. We have to take the square root of 9. What is square root of 9? 3. Let's take b as 3. Right? If I take b as 3, then if we apply Euclid's division lemma, so by Euclid's division lemma between a and b, so what we can write? We can write a as bq. A is equal to bq plus r, where 0 less than or equal to r less than b. This is what Euclid's division lemma says. Here we will substitute only for b, because a is a. We don't know a is any integer, so b is 3. So a becomes 3q plus r, where 0 less than or equal to r less than, what is b? B is 3. So which means a is equal to 3q plus r. So here we are substituting b as 3 in this Euclid's division lemma. Then it becomes like this. Only for b we are substituting, because we don't know a, q or r. Without knowing a, we cannot find q and r. So we know only b, we are substituting only b here, and then the next becomes a is equal to 3q plus r, where 0 less than or equal to less than 3 means r is less than 3. And r is from 0. So r can take the value 0, 1 and 2. R can be 0, 1 and 2. It cannot be 3, because 3 is not less than 3. So r cannot take the value 3. 3 is not less than 3. So r is 0, 1 and 2. Now we will have to consider different cases. R equal to 0, what happens? R is equal to 1, R is equal to 2. Suppose had we taken b as 9, had we taken b as 9, what would have happened here? It would have been 9 here. Then 0 less than or equal to or less than 9. 9 means r would have taken the value 0, 1, 2, 3, 4, 5, 6, 7, 8. So for each value of r, we need to solve cases. We will have 9 cases starting from 0. 0, 1, 2, 3, 4, 5, 6, 7, 8. 9 cases we have to deal with. Right? That will make the problem very huge. So now it is only 3 cases we need to deal with. So first case 1 is when r equal to 0. When r is equal to 0, what happens to this expression? Then a becomes 3q plus 0. I'm substituting r as 0 here. Then a becomes 3q. Now what we have to prove? We have to prove cube of any positive integer. So which means we have to take cube on both sides. So taking cube on both sides. If we take cube on both sides, what a becomes a cube equal to 3q the whole cube. A cube is equal to 3q the whole cube. So a cube equal to, because we have to prove cube of any positive integer. First we have taken a positive integer. A is a positive integer. Then you have to take the cube of that. So this becomes 3q, the whole cube is what? 27q cube. 3q the whole cube means 3q into 3q into 3q. 27q cube. So my a cube becomes, can I write this as any one of the form? 9 into something. 27 can be written as 9 into 3q square. 3q cube. 27 can be written as 9 into 3. So 9 into 3q cube. So 9 into 3, 27q cube. We'll get back the same. So a is of the form 9 into this 3q cube, can called as m, where m is equal to 3q cube. Right? So here obviously r and q and r are integers. So m is also an integer because q is an integer. Right? So we'll say for some integer m, comma, for some integer m. For some integer m. Now a is in this form. So now we should take the second case. Second case is what? R equal to case 2. Case 2 is r is equal to 1. We have to take r is equal to 1 case. When r is 1, this a becomes a is equal to 3q plus r. That is what we have. Right? So my a becomes 3q plus 1 because r is 1. Right? My a becomes 3q plus 1. Now I need to cube both sides. So if I cube both sides, cubing both sides, taking cube on both sides after this. So I'm putting a whole cube. That is equal to a cube equal to, now this is a plus b the whole cube form. This looks like a plus b the whole cube form. What is a plus b the whole cube formula? Where is this? What is a plus b the whole cube formula? It is a cube plus 3a square b plus 3ab square plus b cube. That is the formula for a plus b the whole cube, right? So a is 3q here, b is 1. So I will write a cube, a is 3q, so a cube plus 3 into a square, a is 3q, so 3q square into b is 1 plus 3 into a into b square, which means 1 square, right? 1 square plus b cube, 1 cube. So this will become 27q cube, 3 cube the whole cube plus 3q square is 9q square. 9q into 3 will give you 27q square plus 3 3s are 9q, 9q because 1 square is 1 plus 1. Now if you observe this, we are getting a plus 1 form here. It looks like plus 1. So the one that is before this should be 9 into something. So which means in the remaining these three, I have to take 9 common. So I'm writing the continuation of this here. Fine. So that is equal to 9 into, in these three I'm taking 9 common, then this will become 3q cube plus 3q square plus 1. In these three, if I take 9 common, this will become 3 cube. Here it will become 3q square, 9q. I have taken 9 out, it will become 1. Then plus this one will be there. This one will come here. These three terms are these. So if you multiply, you get back this. Now this is like the form what? 9 into m plus 1. Where m is this entire thing. Where m is equal to 3q cube plus 3q square plus 1. So this entire thing, I am calling it as m. This is 9 into m plus 1 in that form. Clear? So a takes the form a cube. A cube is becoming like this. Right? This is a cube. Now next case. Next case is, I am writing here, case 3. Case 3 is r is equal to, when r is equal to 2, then r is equal to 2, what happens? A is b cube plus r. Sorry, 3q plus r. Right? This one. Let us go back to this. Right? Here we should substitute r is equal to 2. Then a is equal to 3q plus 2 because r is 2. Now we have to cube both sides. Then it becomes 3q plus 2 the whole cube. We are cubing both sides. So that is again a cube becomes, now you need to apply a plus b the whole cube formula, this formula for this. So that is a cube plus 3 into a square b plus 3 into a into b square, b is 2 here. A is 3q, b is 2, that you need to substitute here, plus b cube. Clear? So this becomes, a cube becomes 3q, the whole cube is 27q cube plus 27, this is 3q square is 9q square, 9q square plus into 3 is 27q square into 2 is 54q square plus 2 square is 4, 4 9s are 36q plus 8. Now if you observe this, we are getting a plus 8 here. It's like this form, which means the remaining, the values that are before 8, which are these three, we should take 9 common. So if you take 9 common, this will become 3q cube plus 6q square plus 4q plus 8. That is my a cube. So now my a cube becomes, right? Right? My a cube becomes, now I am writing the continuation of this here. So a cube is equal to 9 into m plus 8, where this whole thing is called as m, where m equal to what? M is equal to this value 3q cube plus 6q square plus 4q, right? That is your m. So your a cube becomes, I'm writing the same thing, 9m plus 8. So in every case, here it is 9m, here it is 9m plus 1, here it is 9m plus 8. So what we have proved? We have proved that the cube of a positive integer is of the form. So therefore we can say, therefore cube of any positive integer is of the form, this is the conclusion, of the form 9m or 9m plus 1 or 9m plus 8 for some integer m, where m is an integer. That's what we are saying. So it can take only any one of these three forms. That's how we prove this. Clear? This is a very important problem, a very easy problem. The only thing that you have to be sure is you need to make, generally we'll take b as whatever you have. 9m means we'll take b as 9, 3m means we'll take b as 3, 5m means we'll take b as 5, 4m means we'll take b as 4. But here 9m means we are supposed to, we generally try to take b as 9, but in that case your r will become 0, 1. Here it will become 9. 0 less than or equal to less than 9 means r will take 8 values. So here we stopped with only 3 values because we took b as 3. So if it is r is more, then try to take the square root of 9. Square root of 9 is what? 3. Take b as 3. Then you will have less number of cases to deal with. Otherwise you will have to write for 0, 1, 2, 3. Then you have to take case 4, r is equal to 3. Case 5, r is equal to 4, r is equal to 5, r is equal to 6. Like that you have to do till r is equal to 8. Had you taken b as 9. If there are more cases, then try to take the square root of this number and check it. Whenever you want to take any cube of a positive integer or square of a positive integer. Fine. So this completes the exercise 1.1. Now we will move to the next page. I am going to page number 8. Right? Page number 8 is, so page number 8 in your textbook, which is Theorem 1.2. Theorem 1.2. So what it states is, that is called as fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Fundamental theorem of arithmetic. So what it says is, every composite number. So what this theorem, fundamental theorem of arithmetic states, every composite number. A composite number means what? A number which is not a prime number and also it is not 1. 1 is not a composite number. Right? A number which is not a prime and which is also not equal to 1. That is called as a composite number. Right? So every composite number can be expressed, every composite number can be expressed bracket factorized. Can be expressed or factorized as the product of, okay, as a product of primes. Product of primes. Primes means prime number. Primes and this factorization. And this factorization. And this factorization is unique. And this factorization is unique. Apart from the order in which the prime factors occurs. Apart from the order in which prime factors occur. Right? So what it says is, every composite number can be expressed or in the bracket factorized as a product of primes, which means prime number, and this factorization is unique. apart from the order in which prime factors occurs. Right? This is the definition of fundamental theorem of arithmetic. Though this definition may be a little confusing, or we will not be able to understand what we are trying to say here, but I will give you example, then you will be able to understand this particular theorem. Right? So suppose I take composite number. Suppose if I take a number as 20. Now 20, this number, we can write this as product of primes, which means we can write this as multiples of primes. So which means how do we do? We'll do the prime factorization. 22, then 10 times, 2 goes 5 times, 5 1 time. So which means my 20 can be written as 2 into 2 into 5. Where each of them are 2 is a prime number, 2 is a prime number, and 5 is also a prime number. So here you should have only prime numbers. Which means 20 is written as product of primes. Product means multiplication. Right? So your number 20 is written, can be written in this form. And this factorization is unique. This is the only way you can write. Apart from the order in which the prime factors occurs. Apart from the order can change. You can write it as 2 into 5 into 2. Or you can write it as 5 into 2 into 2. So you can change the order. But it will have 2 2s and 1 5. That will not change. You cannot write this as 3 into something or some other factors of prime you cannot write. Some other factors of prime you cannot write. Clear? So we will take one more example. Suppose if I want to take suppose 72. How can I write 72 as 72 can be written as 2 36, again with 2 18, again with 2 9, then again with 3 3 3 1. So which means I can write my 72 as 2 into 2 into 2 into 3 into 3. 2 into 2 into 2 into 3 into 3. Right? So which means I can even write this as, if you want, I can write 2 into 2 into 2 means 2 cube into 3 into 3 is 3 square. So you can write it only in this form, 2 cube into 3 square. You can't write it as any other form. You cannot write it as 5 square into something, or we can say, sir, I can write this as 12 into 6 is 72, but 12 and 6 are not prime numbers. So here you should have only prime numbers. Here you should have only prime, because 12 and 6 are not prime numbers. Right? What are the prime numbers? Prime numbers are the number which are divisible by only itself, or 1, or the number which are divisible only by itself and the number 1. Suppose if I have 7, 7 can be written as, or 7 is divisible by only by 7 or 1. 7 is divisible by 7 or 1. If I take 9, 9 is divisible by 1, 3 and 9. So it is not a prime. 9 is a composite number. Prime number means it is divisible by that number, which is 7, or it should be divisible by 1. And 1 is not a prime number. 1 is neither prime nor composite. If you take 2, 2 is a prime number, 3 is a prime number, 4 is not a prime number, because 4 is divisible by 2. So the number which is divisible by only itself and 1, either divisible by 7, 7 is divisible by 7, and 7 is divisible by 1, then 7 is a prime. But 9 is not like that. 9 is divisible by 1, 9 is divisible by 3 also. 9 is divisible by 9 also. So if it was 9 was divisible by only with 9, 1 and 9, then 9 would have become a prime number, but 9 is divisible by 3, therefore 9 is not a prime number. Fine? Okay, these are earlier things that you, so this is what the fundamental theorem of arithmetic says. Every composite number can be expressed or factorized as product of primes, and this factorization is unique. Right? So this also you can write this as, or you can write this as 2 into 2 means 2 square into 5. So this is unique, but apart from the order in which the prime factors are, I can write 5 into 2 square, or I can write 2 square into 5, but you can't write it in any other format. That's what this theorem states. Right? Now is this statement clear? Like every composite number can be expressed. 20 is a composite number, and it can be expressed as product of primes, and this factorization is unique. This is the only way that I can write. Then apart from the order in which prime factors occurs, order can be changed. I can write this as 5 into 2 square. I can write 5 here and 2. That is the order can change. But you cannot have any other number. Like you cannot write 20 as, some 3 into something or 7 into something, or, right? We cannot write. This is the only way we can write. Right? So this is what the fundamental theorem of arithmetic states. So now let's go to the next section, which is example 5. Example 5. So what does example 5 says? In page number, I'll put example fully. Example 5. Right? Page number 9 in your textbook. So what it says is, consider the numbers 4 power n, where n is a natural number. Check whether there is any value of n for which 4 power n ends with digit 0. Right? We have a number. So what is given is 4 power n, where n is a natural number. N is a natural number. Right? Any number in the form of 4 power n, where n is a natural number. Now what we have to check? What we have to check? To check is whether 4 power n ends with digit 0 for any n, which means for any value of n, whether I will get 4 power n will it end with digit 0. We have to check whether it is possible or not. They are not saying it is possible. You have to check whether it is possible or not. Right? Which means, suppose if I have, so I make you understand what the question is. Right? So suppose if you have 4 power 3, 4 power 3 is what? 64. So I have put 3 for n. For n I have put 3. What is 4 power n? 64. Does it end with 0? No. So like that, if I keep on trying, what is 4 power 4? 4 power 4 is 256. Does it end with 0? No. So if I try 4 power 5, right? So 24 to 20, 22 carry 2, 1024. Does it end with 0? So like that, if we keep on trying, will there be any 4 power n? 4 power something, it can be anything, 6, 7, 4 power 8 or 4 power 9, 4 power 10. Like that, if we keep on doing, will there be any 4 power something where the last digit will be 0? That's the question. Actually, it is not possible that we are going to prove. It is not possible, which is we are going to check and prove. Now, proof is that, so what I say is, for 4 power n to end with digit 0, suppose if 4 power n to end with, suppose for 4 power n to end with digit 0, if it has to end with digit 0, for 4 power n to end with digit 0, it must be divisible by 10. Suppose if 4 power n is ending with 0, then the number 4 power n should be divisible by 10, because any number that ends with 0 is divisible by 10. Any number whose unit, whichever ends with the digit 0, that number will be divisible by 10. If you take 20, it is divisible by 10. Take 140, that is divisible by 10. Any number that is ending with 0 is divisible by 10. That is the condition for the divisibility test for number 10. Now 4 power n to end with digit 0, it must be divisible by 10. Right? So which means we can say it means 4 power n should be divisible by 2 and 5. Any number that is divisible by 10, if a number has to be divisible by 10, it should be divisible by both 2 and 5. Only then that number will be divisible by 10. Because the prime factors of 10 is 2 and 5. If 4 power n is divisible by 10, means 4 power n should be divisible by 2 and 5 also. So which means 4 power n should be divisible by 2 and 5, which means that is, or we can say that is 4 power n should have 2 and 5 as prime factors. 2 and 5 as prime factors, which means 4 power n should have 2 and 5 as prime factors, which means when I write 4 power n in this way, it should have 2 and 5. If I write 4 power n is, suppose 4 power 4, 256 should be written in some way, and that should have 2 and 5. Only then it will be divisible by 2 and 5. If it has factors, prime factors, right? 4 power n should have 2 and 5 as prime factors, because then only 4 power n should be divisible by 2 and 5. Then only that 4 power n will be divisible by 10. Then only it will end with digit 0. For 4 power n to end with digit 0, it should be divisible by 10. So any number that is divisible by 10 should be divisible by 2 and 5. So any number that is divisible by 2 and 5 means what? It should have 2 and 5 as its factors. Right? Which means 2 and 5 should be factors of 4 power n. 4 factors means 2 and 5 should divide 4 power n. Which means 4 power n should be divisible by both 2 and 5. Right? But what we have? If we try to write the prime factorization for 4 power n, 4 power n can be written as what? 4 power n can be written as, now 4, take the 4. 4 can be written as what? 2, 2, 2, 1. So which means 4 can be written as 2 square. So 2 square, then power n, which means whole power n. 4 power n can be written as 2 square. 2 square power n, which means it is 2 power 2n. 2 power 2n, which means what? 4 power n has only 2 as the prime factor. 2 power 2n, which means it is 2 into 2 into 2 into, like that it is going for 2n times. You have to keep writing. If it is 2 power 5, you will write 2 5 times. If it is 2 power 7, you will write 2. If it is 2 power 10, you will write 2 10 times. If it is 2 power 8, you will write 2 8 times. It is 2 power 2n, which means, right? Which means, so 4 is equal to 2 power 2n. So 4 power n has only 2 as its prime factor. Which means 4 power n has only 2. It has only 2 here. It does not have any other number, 5 or anything. 4 power n has only 2 as its prime factor. So therefore, and also by fundamental theorem of arithmetic, fundamental theorem of arithmetic, this factorization, this prime factorization is unique. Factorization is unique. This prime factorization is unique. So therefore, 4 power n does not have, which will, see, by fundamental theorem of arithmetic, this is the only way that I can write 4 power n as. That is unique. I can't write any other way. Unique means that is the only way we can write. We can write only in this way. We cannot write it in any other way. Which means I can write 4 power n only in this way. In this way, if I write, it has only 2. There is no 5. But we need 2 and 5. But it has only 2, but it does not have 5. Which means it will not end with digit 0. Right? That's how we are going to put. Therefore, we will say 4 power n does not have 5 as its factor. Which means 4 power n does not have 5. Whichever comes here, there is a factor of 4 power n. Here only 2 is coming. Only 2 is the factor of 4 power n. So 5 is not a factor of 4 power n, because 5 is not coming here. Therefore, if 4 power n does not have 5 as its factor or prime factor. Prime factor. Therefore, 4 power n does not end with digit 0 for any n, for any natural number n. For any natural number n, your 4 power n does not end with digit 0. So they asked us to check, we checked it, and we realized it that 4 power n will not end with 0. Because for 4 power n to end with 0, it must be divisible by 10. For a number to be divisible by 10 means that number should be divisible by 2 and 5. If a number has to be divisible by 2 and 5, then it should have 2 and 5 as its factors, prime factors. But 4 power n has only 2 as the prime factor, which means the 4 power n does not have 5 as the prime factor. When 4 power n does not have 5 as the prime factor, then 4 power n is not divisible by 10, which means 4 power n, sorry, 4 power n is not divisible by 10, which means 4 power n will not end with digit 0. Clear? So this is how we prove that 4 power n for any number, whatever number you put in the power of 4, 4 power 5, 4 power 9, 4 power 18, whatever power of 4, it will never end with digit 0. Right? Like 4 cube was 64, we saw here, 4 cube is 64, 4 power 4, 262, 4 power 5, 1024, so nothing will end with digit 0. However, how many ever powers you put for 4, it will never end with digit 0. Fine. So we will stop the session here. You can watch my next video for the continuation of this. Thank you for watching.